Welcome to the Phenomenological Alliance channel. In this video, we will discuss the next question that phenomenology problematizes in the field of natural sciences, namely the problem of the theoretical domino effect.
One of the essential characteristics of oscillatory motion is reflected through the so-called Doppler effect. The Doppler effect is the change in pitch observed when a sound source moves relative to a listener. After Young's and Fresnel's work, it was accepted that light is also of a wave nature. This led to expectations that in luminous phenomena, there must also be a change in the spectral composition of light when a light source changes its distance from the observer. However, no one observed a change in the color of light sources during motion. This fact was attributed to the immense speed of light, as alterations in speed achieved on Earth have an insignificant impact on the speed of light. The first attempt to experimentally verify the Doppler effect in optics was made by A. A. Belopolsky in 1900.
The apparatus is based on the principle that the path light travels depends on the angle between two nearly parallel mirrors. When the wheels rotate in the same direction, the path differs due to the different angles of reflection compared to when they rotate in the opposite direction.
The light from a mercury lamp is reflected from the blades and analyzed with a spectrometer. It is noticed that the spectral lines of the mercury lamp show shifts depending on the direction of rotation. From this, it can be concluded that light exhibits a change in frequency in the form of the Doppler effect, similar to other oscillations. Specifically, the variation in the lengths of the traveled paths alters the wavelength of light. Previously, it had been observed that the light from planets within our solar system did not exhibit any spectral shift. Consequently, a thorough analysis was conducted on the lights emitted by stars and galaxies. In 1912, Vestos Lippard discovered that light from distant galaxies displayed a spectral shift akin to the one observed in Belopolsky's experiment. This shift was interpreted as an indication of galaxies moving away from Earth, providing support for the scientific validity of the Big Bang theory.
In the mentioned experiments, let's incorporate the rules of visual perception. Let's pay attention to how moving images affect visual perception. Let's examine the ways of blending colored impressions using the color wheel. The shades of gray depend on the speed of rotation. The faster the rotation, the lighter the wheel appears. Thus, we notice that the stroboscopic effect can change what mainstream physics call the spectral composition of light. Now, let's analyze Belopolsky's experiment. Belopolsky's initial premise is that the path light travels depends on the angle between two nearly parallel mirrors. However, staying in the sphere of phenomena, we can notice that two nearly parallel mirrors shift the field of view, depending on the angle between mirrors. The path light travels is already an addition to obvious fact. Moreover, when we use a prism to observe the white light obtained by mixing yellow and blue, we notice that with the help of the prism, we see the original image again. Through a narrow slit, we observe the blended impression of a yellow and turquoise circle, which we can separate again with the help of a prism. Regarding the image shift, it doesn't matter whether we are looking at the original image or its parts obtained by spectral analysis. The prism creates the illusion that only the spectral lines are shifted. But the entire image is shifted, not just spectral lines. Now, instead of watching a rotating wheel, let us look at a sparkling object, the result of the spectral analysis will be different if the object sparkles than when the object does not sparkle. When we look at the sparkling stars, the result of spectral analysis will be different from when we look at the planets that do not sparkle. The light from stars will exhibit a changed spectrum when analyzed with a prism, whereas the light from planets will not. From a phenomenological perspective, one might examine the displacement of the field of view of stars and galaxies due to the Earth's motion, as we observe them from a planet in motion. The Doppler effect in optics, which leads to the conviction of the motion of galaxies in cosmic depth, is a hypothesis that extends well beyond the framework of phenomena.
The basic question that phenomenology examines is the structure of consciousness experience. The application of phenomenology in physics demonstrates that all theories and hypotheses that are not the descriptions of facts are destined to collapse, resulting in the effect of the theoretical domino effect. Hence, the phenomenological approach establishes methodological guidelines comprising 3 essential steps. To the phenomenological approach, history is not a mere record of past events. Instead, it serves as a tool for comprehending a consciousness distinct from our contemporary perspective. Without this understanding, we remain unable to fully grasp our own convictions and limitations. In this stage, the phenomenological approach emphasizes gathering the most precise descriptions of the phenomenon, giving equal weight to both subjective experiences and supposed objective descriptions. Experiments are not designed to prove a hypothesis, but rather to present observations more clearly. After enough collected observations, a common emergent pattern, or primal phenomenon of the given scope of research, begins to emerge. In this stage, the unity of manifold correlating experiences reveals itself through intuitive cognition. Using such methodological guidelines, phenomena interpret phenomena, without the need to isolate natural laws as assumed causes of phenomena. This avoids complex interpretations, based on a series of theories and hypotheses.
The examples above reveal a significant misunderstanding of fundamental phenomena. Modern science, with its hypothetical methodology and current stage of development, is not mature enough to comprehend complex questions such as the genesis of the universe. At the end, let's try to answer a seemingly simple question. What is light, actually?